So this is a super short lesson. Basically, what we do is we use a tangent line to approximate the actual value of something. So sometimes when they want you to know the effect of a small change on a bigger function, like how small does a change in an angle affect the distance of a basketball shot? How are revenues at the box office affected by a small change in ticket price? Or the cube root of 27 is 3. How much bigger is the cube root of 27.2? What we do is we make a tangent line approximation for it, and by making the tangent line, we can estimate kind of how big of a change in x will make your change in y. Okay. All right, so everybody knows how to make a tangent line, right? The way to make a tangent line is y minus, y1 equals m times x minus x1, right?
Oh, thank you, Jackson.
Everybody's got that, yeah? And y1 and x1 come from the function f of x, so it's y minus f of a equals, and then the m comes from the derivative at a, x minus a, right? Okay, so what we call a linear approximation, and when you solve for y, we usually label it L of x because it's the linear approximation for this function. So L of x equals, and you just solve for y, so you bring this f of a over to the other side. So it's f of a plus f prime of a times x minus a. But it's the exact same thing as just making a tangent line and solving for y. Okay. All right? Great. So here's what we're doing. Here's a visual of what we're doing. We have a curve here, right? And we make a tangent line at a location at A. Okay. And then we use that tangent line. So instead of finding a value for on the original curve, we use the tangent line to find an approximate value for your function, and the actual value is going to be a little bit off. But if you're close to your original location of your tangent line, you won't be off by that much. But what you can do is you can calculate the error in your approximation, or how much of an effect changing a small thing will do on it, depending on if your slope is large or small at that point. Is that weird? Did I explain that right or no? Are you confused?
I'm confused as to where this might be more useful than just going and straight up evaluating the equation.
Because it's a lot easier to evaluate a linear function than an original function if the function is too large. You know, like for computing especially, is like approximating a line is much easier than actually plugging it into a really difficult function if you know like the rate of change and a value close to it.
Yeah. But if you have a really difficult function, taking the derivative at a given
well, it's not taking the derivative if you know the rate of change at that location.
So if it's already enough.
Yeah. Okay, so what we're going to do, we're going to do some really easy versions of this. So we have this function 1 over x, and we're going to use it to estimate the value of 10.2. Okay, if I want to estimate the value of 10.2, I'm going to make a linear approximation at what value, do you think? Let's make it at 10, x equals 10. So we'll make a linear approximation at x equals 10 so that when I approximate 10.2, it's not that far off from where my tangent line is. Okay. All right, so what do I need for a linear approximation? I need L of x equals f of a plus the derivative at a x minus a. Okay? So, f of a is 1/10. F prime of a I have to figure out. So what's the derivative of 1 over x? Yeah, negative 1 over x squared. So f prime of 10 is negative 1 over 100. Okay, so 1 over 100 times x minus, and then a was 10. All right, so there's my linear approximation. That's done. Okay, and then we're gonna plug in 10.2 in for x and solve for what my tangent line would give me. So my linear approximation at 10.2 is 1/10 plus 1 over 100 times 10.2 minus 10. Oh yeah, sorry, I forgot that negative.
Yeah, of course.
Thanks. Okay, what is it?
Small.
.98. Okay, and then how good is our estimate? So if I actually did 1 divided by 10.2, I'd get 0.9803. So my actual function at 10.2 was 0.98039.
What was the point?
2. Yeah, thanks.
Sounds good.
I'll put my point here. Ignore that. Delete.
Sorry,
Okay, pretty good, right? And then I'm going to ask you one follow-up question. How good is our estimate? Our estimate's pretty good. One follow-up question. Since the linear approximation is smaller than your original function, would the graph, or would my f of x be concave up or concave down, do you think?
It's concave up.
It's gotta be up.
Why?
Because it's slowing down its rate of change from ours.
Right. Remember that if our original function is above our linear approximation, then our tangent line lies below, and if our tangent line lies below, then our curve is concave up. So a lot of times, and we'll do a problem like this where it's backwards, where it gives you the concavity of the curve, and then it asks you if your approximation is greater or less than your actual value. And that's how you can explain. Okay, got it? All right, just the back left to do, and then we're done. The Bonzo Pizza Company claims its pizzas are circular with a diameter of 50. What's the area of the pizza? That's easy. Bonzo does not serve any non-circular pizzas.
2,500 for
It is.
pie.
No Litos for Bonzo.
Oh wait,
Nice.
25
Yeah.
squared is now 2,500.
They just sold these
25.
all
Square pizzas.
things got over the pizza place not there.
I think we gotta open the pizza.
1963.495.
Yeah, it's a waste of resources. Make a circle pizza.
Centimeters squared. Okay. Estimate the quantity of pizza gained or lost if the diameter is off by at most 1.2. So what we can do is we can find, we can make this area equation in terms of diameter. A equals pi times diameter divided by 2 squared. And then make this 1/4 pi d squared. Okay. Everybody good with that?
No,
Then,
wait,
no? No.
Sorry, I was.
Okay, now we can take the derivative, so dA dd, because we're the derivative of a with respect to diameter, is 1/2 pi d, right? Yes? Okay, and then if your diameter is off by at most 1.2, then we can say that the change in d is 1.2. So this is dd, the change in diameter. So our diameter is off by 1.2. So if we plug that in for dd, and then plug in 25 for, no, 50 for RD, not R. Then dA will equal 94.247. Oh, I truncated, guys.
Oh,
So that's how much your diameter, your area could be off by if your diameter is off by 1.2. So Bonzo could be jipping you 94.247 centimeters
So why?
if he
Who
changes
makes
his
half-meter
diameter.
wide pizzas? Pizzas that are half-meter wide. That just doesn't seem.
Why wouldn't you?
That's not that big. That's big.
That's like
People make pizzas this big.
No, they're this big.
half a meter.
That's probably about.
No, that's like a full meter. That's like a meter.
That is not a full meter.
16.
This one, which
No,
one?
it's around
Where's my
1.5
meter stick?
feet.
Oh, there's a meter stick in the
Gosh.
back.
Grab the meter stick.
That's not that big.
Josh is about 2 meters tall.
This is definitely not a full meter.
That's more than.
And then half
That's
of
more
it.
than half of it.
Half of it.
yeah,
Yeah, that's a regular large pizza at Domino's.
Miss Moore, where's your favorite pizza place? Domino's.
No,
Church Street?
I like Church Street. Domino's has gotten better though.
Yeah.
Yeah.
This one, would you sell pizza at Muy Bien?
No,
No, it's 18.
it's an Asian Mexican fusion.
Where does Italian
Pizza doesn't-
Because Berkeley and I are opening a pizza place right next to you.
We don't have a name yet.
No.
we
But
have a
Sam said she
strategy.
wanted to open a pizza
Yeah, that
place.
too.
So are you gonna go in with Sam? Sam says she's gonna back me.
Oh,
Back
that's
in you.
Yeah, she's
already have
gonna.
a signed
I'm gonna
contract?
start my
Running out of business.
GoFundMe.
We'll probably burn.
Miss Moy, we're all here to support you.
Thank
This
you.
is what you can optimize the size of your
Did she
pizza.
tell you her, if she wins the lottery plan?
No.
Well, she's opening Muy Bien, then she's opening a pizza place, then she's going to Greece. That's it.
Step 1, step 2, step 3.
Yeah.
I like that plan.
So this is gonna be open.
Okay, let's finish
Yeah,
up.
working.
No, it's working.
Find tangent line approximation for 1 plus x near x equals 0, then use it to approximate the value of 1.02. So we're going to make a tangent line at 0. That is L of x equals f of 0 plus f prime of 0 times x minus 0, right? Tangent line approximation. Okay, then f of 0 in here is 1. Okay, we got to take the derivative of this. So f prime is 1 over 2 root 1 plus x. That's it, right? And then plug 0 in, so 1/2. So 1 plus 1/2 x minus 0. Tangent line approximation done.
Nice.
use it to approximate the value of 1.02. So set these two equal square root of 1 plus x equals square root of 1.02, and what does x have to be? 0.02. Okay, so that's what we're going to plug into x here, 0.02, and so our approximation at 0.02 is 1.01. There's our tangent line approximation. Easy peasy? So easy. Well, actually, what is actually 1.02? Square root of 1.02 is
Compute optimization.
1.099. 0099. This is not too bad. Because it's close. Like they look.
Like you have to, like if they ask like if it's good, we just go back and do that.
Yeah,
Okay.
the but based on this, is your function concave down or concave up?
Down.
Why?
Because the tangent is greater than.
Tangent is greater than your actual, so that means that you got a tangent line on top of your curve, so it would be concave down. Cool. All right. Next two examples. This is nice. F of 2 is 3. The slope at 2 is -2, and the second derivative everywhere is -5. Approximate the value of f of 2.01. So let's make a linear approximation at 2. So that's f of 2 plus f prime of 2 x minus 2. There's our linear approximation equation. F of 2 is 3 plus f prime of 2 is -2 x minus 2. We're approximating the value of f of 2.01. So what should x be? .01, right? Right, because this is f of x. So that we can't really solve because it's just f of x and x. So L of 2.01 equals 3 plus -2 times 2.01 minus 2. And you get 2.98. Okay. Is this an over or an underestimate? Yeah, why? Yes. So you want to say overestimate, and then because f double prime of x is negative, so f is concave down. If it's concave down, your tangent line's going to be on top, and if your tangent line's on top, then it's an overestimate. Easy? So easy. Okay, y equals 2x minus 1 is the linearization of f of x at x equals a. So it's here at 1. So what is f of a? What's the y value? 1. And what's the f prime of a? Slope is 2. Okay, estimate f of 1.2, so we'll plug 1.2 into our linear equation. Did I do that right? No, I don't think it is. 1.4. 1.2 is here. Yeah, it's about 1.4, I guess. Is this an over or an underestimate? Underestimate. Well, we can't really justify, so cross that out because I didn't tell you what the original function is, even though you can see that the curve is concave up, so.
Are we allowed to say that the curve is concave?
Not unless not unless they give you some definitive, like.
You're not allowed to say it's
Yeah.
the same graph.
Yeah. Okay. And last problem. Show that y equals 1 plus kx is the local linearization of y equals 1 plus x to the k. Using this, approximate root 1.1.
Yeah.
Oh. All right. Y minus, well, or y equals maybe L of x, if you want to. So there's my linearization, right? What is my y value's gotta be 1, right? F of a equals 1. And f prime of a's gotta be k. And then this will be x minus 0. I don't think I did that right. This one is my y equals equation. So at a equals 0, y is 1 plus 0 to the k, which just equals 1. And then my y prime is k times 1 plus 0 to the k minus 1. Or just k. Ah, that's why. So that's why these two are equal. Y equals 1 plus k times x minus 0. These two are now equivalent. So that's why this is the local linearization of this function. All right. Yeah.
Why is A 0?
I just made a 0.
Wait,
You set a equal
No, that's the one that worked. Otherwise it wouldn't have worked. If I made a
So it's
equal
only
2,
local
I should
linearization.
probably say add x equals 0. Let's say this. Let's add in add x equals 0. Sorry, guys. Okay. If I set these two equal, 1 plus x to the k equals square root of 1.1. What should k equal and what should x equal in order for those two to be equivalent statements?
0.1.
K is 1/2 and x is 0.1. Okay, and then if I want to approximate root 1.1, then root 1.1 is approximately 1 plus, plug 1/2 in for k, 0.1 in for x, and we get .05. And that's our approximation. That's it. Just make some tangent lines and use it to approximate things. It's not gonna be fun.
The standard quiz.
This one?
Yeah, or the test.